I want to talk to you today about CMAF low latency streaming, and thank you to Andreas Sidronius for actually an excellent introduction to my topic as well. I'm going to go a little deeper into some of the technology behind adaptive streaming, and always bearing in mind a live linear use case and sports and broadcasting. So I work at Akamai, and I want to thank also my colleagues for a very hospitable stay here in the Nordics, as to Iwan for the opportunity to address and speak with you today. So again, I just want to set the stage. A lot of people, when we say the word latency in English, a lot of us talk about the connection latency, the RTT. That is not the context in which I'm using latency today. I'm using what we would call the live stream overall latency, and we have many synonyms for this in the industry. We call it end-to-end latency, glass-to-glass, or hand-waving latency, which is how we traditionally test it. You wave your hand in the camera and you see when it appears on your phone. So this is what I'm addressing today when I say the word latency. So this is a chart you may have seen from our colleagues at Wowza. We've all borrowed it, and I'm reusing it again here today. It shows the continuum of latency broken out by different streaming solutions. And this is a somewhat traditional and retroactive view of these. So if you look at where we are in 2017, you'll see a lot of solutions that are 20 seconds and up for OTT. This is major broadcasters, live linear solutions, and even sports events. But what you're going to see as we move into 2018 is this is going to shift downrange. We are going to come down to the 3 to 30-second range. And there's different reasons to sit within this paradigm. Some people need to be very close to live if you're betting or gambling or your sports. If you have no other frame of reference for your live event and no social media, you're better off being 30 seconds behind. It's a safer, more stable place for your live stream. But what we have are different tools to allow us to sit within this boundary. And interestingly enough, we can take the same live stream and choose where we sit within it. So different applications on the player can choose where they want to sit in terms of live latency. So here's some data collected. The one on the left is slightly old, 2016, but this mirrors very closely the data Anders was showing you. This was in Germany, a study done by Thomas Stockhammer at Qualcomm, where they're comparing the latency of some live events, and they used satellite as a baseline here. So satellite is time 0, and then you see DVB-T 2 seconds above that. That was satellite SD, but all the streaming servers significantly 8 to 56 seconds behind the satellite, and in some cases the terrestrial broadcast. Very similar event in the United States. This was our political debates with a tragic outcome back in 2016. And you'll see that the baseline here is not satellite, but it was an audio transmission, radio. So radio is pretty near real time. And these are the offsets from that. So cable was 10 to 12 seconds, and then the streaming services going up in terms of latency. So this is that 2017, 20 to 50 seconds latency. And I think a lot of you, if you come from the broadcast space, you have in your head that this is how OTT is going to work. There's nothing we can do to change this. And this is not the case. So let's look at some facts about latency. Stream start time is when I press the play button and the stream actually starts to play. And live latency or hand waving latency is the delta between the event occurring in real life and me seeing it on my screen. These two items are not related. So a stream can take 5 seconds to start, but then be 2 seconds behind live. Or conversely, it can start very quickly, but be further behind live. So they're not coupled. You don't need to start quickly to be close to live. And I'll show this to you in a practical example. A live player has only one chance to build its buffer, and that's before it starts playback. A VOD player can start playback very quickly, and then in the background, it can build a large buffer because media is available ahead of time for it to download. A live player doesn't have that luxury. Media is being produced by the encoder at 1 second per second, and it's decoding it at 1 second per second. So its buffer never increases in size once it starts playback. You can do some tricks with adjusting the playback rate. So you can retard the playback rate slightly in order to increase your buffer size, but these are minimal variations you can do. So mostly you have to commit to your buffer before you start a live stream. And traditionally with segmented media, which is HLS, Smooth, Dash, Adobe, HDS, we've had a latency that is some modulus of a segment duration. And I'll go into reasons why this happens. And it's always a trade-off. Anytime you want low latency, you're going to have low buffers. Your buffer cannot be greater than your latency. And as has already been mentioned, the internet's an unstable place. So the smaller your buffer, the higher the likelihood of some perturbation taking you out of that regime. And there's various ways we can accommodate for this as we move through it. So let's look at a typical example here. We've got our encoder, we've got time running from left to right, and I have an encoder that's producing segments at 2 seconds each, and we're going to observe it halfway through the middle of the 5th segment, okay? And it doesn't matter if this is HLS or dash or smooth. The logic here is identical. This is segmented media. So an Apple player or AV Foundation, if you put your M3U8 into Safari or in QuickTime Player, it has a rather conservative starting algorithm where it says, go and find the last 3 segments that are fully formed and start playback. So it would grab segments 2, 3, and 4 in this example. And when it does that, it commits itself to 7 seconds of latency, because that segment number 2 was actually produced 7 seconds ago. But it's got a nice big buffer, 6 seconds of buffer. And Apple has decided that this is where they want to sit on the robustness versus latency curve. The bad part about this is everyone, all of us, need to sit at this same point if we use their buffering algorithm. And there's no knob or tweak you can use to adjust this. This is baked in, if you use the default algorithm. Now, of course, you can go and build your own player and choose to start somewhere else. So a reasonable place to start might say, okay, I'm going to take segment 4. That's fully available. And I'll start playback. So now I cut my latency in half compared to the Apple starting algorithm. But I've also sacrificed my buffer. It's come from 6 seconds down to 2 seconds. But my latency is now only 3 seconds. And in fact, if you look at this carefully, you can decide, hey, I can reduce the latency even further by waiting and grabbing segment 6 or segment 5 immediately when it's done being encoded by the encoder. So if I wait 1 second, I can grab segment 5, and now my latency would be 2 seconds. So this is an example where actually increasing the stream startup time lowered our overall hand-waving latency. So the interesting part about this is we have the same stream coming out an encoder, but the latency can vary from 7 seconds down to 2 seconds, purely based on the player starting algorithm. And I'm not sure a lot of people, we tend to focus on the encoder and the latency and the segment duration. We don't focus so much on what our player is doing when it actually starts up. So in the broadcast continuum of taking an encoder, uploading it to a CDN, the CDN propagation, last mile delivery, player buffer in total, as I mentioned, traditionally it's been quantized around the segment duration. And if in the old days, Apple put out the HLS encoding guidelines, and they said, thou shalt use 10-second segments. These are really big seconds. And when you plug 10 seconds into this, you get 50 seconds out the other end. And that's reflected in real-world data. We see that happening in the European and the US data that I just showed you previously. Now, what a lot of people are doing, Apple have since revised that guideline, by the way, to take it down to 6 seconds. That was about 1.5 years ago. But even then, if we drop the segment duration to 2 seconds, there's a linear reduction. Our overall latency can come right down to 11 seconds without changing any other part of this distribution chain. Now, you can argue, well, is my visual quality the same with a 2-second GOP versus 10 seconds or 2 5-second GOPs? It will be slightly reduced, but there are a lot of broadcasters now who are looking at 2-second segments as the sweet spot of visual quality versus latency as a trade-off. So without changing anything, you can be in the 12 to 14-second range of glass-to-glass latency by simply reducing your segment duration to 2 seconds. Now, there are a number of options for live stream delivery, and I just want to go through some of them and look at their applicability in terms of latency. So typically, you always have an encoder. It's producing some input format. It goes to a CDN. There's an output format, and it goes to a player. I was in Beijing last month. It turns out in China, everyone uses RTMP in and RTMP out. And in the United States, we're starting to phase that out, mostly because RTMP requires Flash Media Server, which is a license to Adobe, which is a less scalable network. But in China, they have open source implementations for RTMP. There's no royalty going back to Adobe. And this, in fact, gives low latency solutions. So you'll see 3 to 5 second delay there, and there's this huge ecosystem built out. But it's being deprecated somewhat in the US and Europe, even though RTMP, as you'll see, is still favored as an input format. So another option would be RTMP in and then converting to HLS and dash dynamically. This is done by quite a few providers, including Akamai today. So you can actually get a reasonably low latency, 4 to 6 seconds range. And again, I'm showing you the lower end of the latency. Anders previously made an excellent point that stability is maybe more important over the duration of the stream. So you want to be careful not to always be at the bleeding edge of your latency. But the advantage of low latency is you can then trade it off for stability, and we'll get to that. Another option would be RTMP in, WebSockets out, which I think Wowzer use. And your latency can get really low here, 2 to 5 seconds, again, depending how your encoder is producing RTMP. What's very common for a lot of linear broadcasters is HLS or dash in and HLS or dash out. The latency, again, with higher, if you go to 1 second segments, you can get 6 to 8 seconds quite easily, and this is European distribution or even transatlantic distribution. There's a variation on that, which I'm going to cover in this talk today, which is CMAF low latency chunking. And this is where we can take some of the benefits of ISO-based segmentation formats and then decouple the overall duration from the segment. And we can get down in the 1 to 3 second range using this. And if you really care about speed, use WebRTC in and WebRTC out. These are now open standards. Safari just adopted them. There's some trade-offs with WebRTC that I'll go into now, but you can get sub-second latency globally. I was testing a stream published in Boston, playing it back in Bangkok, and it was 450 milliseconds of delay. So let's look at the output formats in terms of their applicability to some business cases. So the output formats are across the top. I'm going to look at playback support in HTML5. So I've put RTMP as a no, because typically you need a flash client or you need some native client on a mobile device to play it back. But all the other formats, you can play back natively inside an HTML5 player. And the industry, at least on the OTT side, is moving towards HTML5 first as a playback and player environment. So some strong benefits for formats we can consume directly in a web page without having to install a player. The latency I marked WebRTC, it's very low. The HLS or dash is medium, depending, again, on the player that you're using to play it back. But the rest are quite comparable in terms of latency. Can you do multi-bitrate playback? So WebRTC, no. In fact, your quality varies quite dramatically with your throughput that's available to the client. WebRTC WebRTC standardizes the latency and it sacrifices quality in order to do that. Whereas the other formats will promise whatever quality you deliver, they will deliver that and they will sacrifice latency in return. So different paradigms. I put WebSockets no for multi-bitrate playback because typically there's some discontinuity when you switch your WebSocket streams, although someone probably has a smart solution that allows you to do that. DRM, already been raised. This is interesting. You can't do DRM with RTMP. I put no. You can do Adobe's default REM, but it's default to DRM, but it's pretty much dying. It's only supported in Flash Player. WebRTC is also not DRM supported. It's secure in its transport, but once the content's received on your device, it's in the clear. Do you have full control over the startup logic? Maybe with HLS or dash, depending if you control the player or you're allowing what's called a type 1 player in the W3C context to play it back for you. But typically with the others you can. WebRTC you don't have control, but it's so fast it doesn't matter. So that's not really a negative. And what I mentioned earlier, quality assured delivery. If I put 720p in, 1 megabit per second to the first 4 formats, I'll get that out in the player. It's lossless delivery. The player may have to rebuffer to play that, but it will play the quality you put in. WebRTC is different. I put in 720p, 1 meg per second, I might get 480p out on my client, and I don't have control over that via the API. But there's many reasons. If you only care about very low latency, WebRTC, despite all the red there, might still be a good application for you. But I want to go a little bit into CMAF, HLS, and dash, because that's the subject of the talk here. Because it is cacheable by servers and also playable by older devices. And when we talk about scale, Akamai just did a live event, 17 terabits per second for a single stream. That's one stream, 17 terabits per second. So you really have to think carefully about the cacheability and the scalability of your low latency solution. So we like these ISO-based segments, but how can we reduce the latency? I'll skip through all these because these are pretty much traditional. How can I reduce latency? Well, adjust my encoder settings, don't use B frames, drop them out, reduce the segment duration, have your encoder close to your ingest point, make sure your CDN's designed for very fast transfer, reduce the last mile, and reduce your player buffer. But let's look at CMAF low latency segments. So what is CMAF? CMAF was essentially, I was going to say collusion, but it sounds negative. It was cooperation between two former foes, Microsoft and Apple. And traditionally, Apple has used TS segments and continues to use TS segments today, whereas Dash and the rest of the industry, and Smooth in particular, went to the ISO-based media file format. So we're talking the actual file container that they used to deliver the video. And these were incompatible. So companies were having to produce two sets of media on the storage systems, and CDNs were having to cache it and deliver it out for the same set of content. So Microsoft and Apple got together and said, hey, can we agree on a common file format? So we're not going to change HLS or Dash manifests, but they're going to refer to a set of files that we can share between the two. So this happened back 2015 into 2016, and a new standard was created by MPEG. It was originally called Common Media Format, which makes sense. They added the word application in there to confuse us all. So it's Common Media Application Format. It's not an application that runs on your phone. It's a file container that holds audio or video content. And it's pretty much, it's done. It's in draft status. You can go and download a copy of it today. And it's magically supported on all your Apple devices for the last 2 years. So the big difference with CMAF, it's essentially taking the Dash file container, but constricting it further such that Apple agrees to support it, and Apple have done a lot of engineering to bake it into their hardware and software. So it is, as its core, an ISO-based media file format, which you can call a fragmented MP4. It supports common encryption, which is important. The CMAF standard references the MPEG codecs, the AVC class, which is 80264 and then HEVC, but you're allowed to add in other codecs. So as a group I work with, we're adding in VP9, we're adding in Dolby AC4 into CMAF. It supports a number of captioning standards, and importantly for this discussion, has a low latency mode of encoding, which is quite interesting. So a CMAF fragmented MP4 contains this object. The lowest object here is called a chunk. Okay, I won't go into the objects, but it's typically, there's a MOOF, which is an index into the audio and video content. And then one or more chunks make up a fragment, one or more fragments make up a segment, and that's what we deliver. Now, typically, when you make, say, a 6-second segment, you start off with a MOOF, you start off with a keyframe, which is the black box there, and then you have 6 seconds of your data. So the encoder makes all 6 seconds and then sends it to the CDN. In so doing, it's incurred 6 seconds of latency because it only sends the first byte after the last byte has been made. What the low latency encode mode of CMAF says is, make a MOOF, keep my one keyframe every 6 seconds, but make a short section of MDAT, and this might be 60 milliseconds or 100 milliseconds long, a couple of frames. Make that, send it out to the CDN, and keep producing it in this format. And if we do that, we can get a benefit. So let's go back to that example I had previously. So our good case there was segment number 4 with 3 seconds of latency. So what if we broke each of these 2-second segments into 500 millisecond chunks? In reality, they're smaller, but I can't fit the text in if I do that. So just imagine there's 4 of them every 2 seconds. So we're starting at time now. We still have to start with a keyframe. So we could go and grab it's going to be hard for you to see it, but we can grab 5A and 5B, which is the chunks holding the data. So notice we're grabbing chunks that the encoder hasn't finished making the end of the segment yet. But when we do this, we now have 1 second of latency, and we can start playback. We also have 1 second of buffer, so we can't have both, okay? But if we care about latency, we can drive our latency down to 1 second. And just as before, we can reduce the latency even further by choosing to wait. So we can wait until segment 6 is available, and we can grab the bytes at the moment they're made by the encoder. So if we wait our 1 second, now we'll have less than 500 milliseconds of latency. It'll start decoding somewhere between 0 and 500 milliseconds. So remember, we went all the way from 7 seconds down to 500 milliseconds just by changing how we encode the content and how we play it back in the player. So I try to put a diagram up here. So if we look at a standard production, the encoder makes it, it goes over to the CDN, and then the player requests it. And that's our typical workflow. So if we look at this low latency encoding mode, it looks more like this. As soon as the first bytes are available or given to the CDN will propagate them out to the player. Obviously, this requires some quite precise timing on the player now. The player needs to know when these bytes are actually available in the encoder. And there's a number of tricks and schemes. I won't go into this talk, but I can discuss them in the coffee break for how to do this. So I'll run these side by side here, and I'll also put a little video that will start playback when the actual player would play back. So here we go. They're in a race. This one has now started to play back as soon as it got the first bytes. That one's still going. And you'll notice they have about a 4-second difference. And this is exactly the type of delta or benefit we see when we deploy this in the field in practice. So if we go back to our chart from Wowza, where do you want to be? You don't want to be at 30 seconds, really. If you're in sports, news, broadcast, gambling, any type of live linear, there's no reason to be there today in 2018. You can comfortably, with 2 seconds, be in the 10 to 12 second range using HLS or Dash. If you drop down to 1 second segments, you'll have a quality drop-off, but not as large as you might imagine. And you can get to the 4 to 8 second range. And I'm talking highly scalable streams now, 500,000, 1 million or more concurrent users. And then if you really want to push the boundaries, you can be in the 1 to 3 second range with these CMAF low latency chunks. And anywhere, 500 milliseconds or sub-second even, WebRTC is a viable alternative for you. So I didn't want to do live demos on the stage because they usually fail, so I recorded some when they were working. But these are actually working, so I can show you them in the coffee break. This is traditional HLS. So remember I mentioned 1 second segments, and if we stop, we got about a 7-second latency. So this is just an encoder in Boston, one side of the United States. I'm playing it back in San Francisco on the other. And this would be a typical live distribution. This will actually beat cable delay in the United States without doing anything fancy here, because we have slow cable in the United States. It won't beat European satellite. Here's the same thing with MPEG Dash. I think this is about a 5-second delay. Again, the protocol describing the content is not that important as how it's encoded and how the player chooses to play it back. Here we have WebRTC. You'll notice this is sub-second now. So these are 3 different encoders I have pointing at the same clock in Cambridge. Now this picture looks really nice because it's static. If this was a motorcycle race, we'd be paying quite a large quality penalty in order to get our latency this low. Now here we go to the CMAF low latency. So this is an encoder I work with Harmonic. The encoder's running in Paris. And I was playing it back in Stockholm where I recorded this. And you'll see we have about a 3.5 second latency. What's interesting is these are 6-second segments. So our total end-to-end latency is less than our segment duration. So we've decoupled our latency from our segment duration. This was another example we did with the EBU in Geneva, publishing back to Paris and then Akamai server in Paris and then back to Geneva. These were, again, 6-second segments with 2-second GOPs, and the chunks were 1 frame in size, 40 milliseconds. And this is Brahm. You probably know him. You'll notice the delay here was about 1.5 seconds. Oh, 1 second. Sorry. And here's a demo I can, again, show you in the coffee break. We have an encoder running on an Azure instance in Tokyo using a GPAX Dashcast X encoder, transmitting over Akamai all the way here to Stockholm. And you see our latency, well, not to Stockholm. This was to San Francisco where I recorded it. And we're pretty solidly sub-second. It's about 536 milliseconds there. And this is a player I wrote that very carefully figures out when to start, and then it starts playback. And it's playing as fast as it can. But per the comment earlier, would I run a broadcast service at this latency? No. But what I would do is I would set it back maybe 2 seconds or 3 seconds. And then I would have 3 seconds of latency, 2.5 seconds of which is actually my player buffer. And that's where I want my latency, in my player buffer where it's protecting me from variance in my throughput. So some summary points: smaller fragments, generally better in terms of hand-waving latency. Low latency requires you to modify your player behavior, and there's a lot you can do within that to reduce it and make it stable. Player startup time is, in fact, one of the largest contributors. Our CDN in that example is only adding about 400 milliseconds to transit the whole CDN. So most of it's encode delay, player buffer. Low latency chunks, I think, offer great potential for reducing latency at scale while still using a transport scheme that is compatible and backwards compatible with existing players. Because if you're requesting a CMAF chunk that's further than 1 segment duration behind live, you simply get the whole chunk as you would have in the past. So a player that's operating 3 segments or 4 segments behind live notices no difference. And WebRTC is interesting. If it were scaled out into a broadcast network, which we haven't done yet, but others may, it offers potential for robust sub-second streaming. And my last slide, I just wanted to close. I've been talking this whole time about latency as if it's evil and we want to get rid of it. But there's quite an artistic use of latency. Was done by this band called the Academics, and you can go look them up on YouTube. So they were publishing themselves through Facebook, and they noticed there was about a 20-something second delay using Facebook Live, at least when they did this demo. I think Facebook have tightened it. So they said, hey, can we use this latency quite creatively to start layering in some music? So you'll see them starting this, and then you'll see the lead singer comes out, and he just seems to shout into the microphone in the absence of anybody else. So you'll see their stream is now appearing in the background. And you've seen guys do this on the stage where they play one track and then they play another track and another. But here they're actually using live stream latency to do their layering. A, O, A, O. So that sounds a little bit out of context, but you'll notice he's now come into his own loop back on the live stream. And they were very clever. They were able to adjust their song and their cadence to match the latency, which I think is a lot harder than they're making it look. And then, as you can guess, he'll start coming in as the singer. And I'll save you watching all of that. Just skip forward. That's actually 5 layers of latency all stacked on top of each other. But anyhow, quite an impressive use of latency, and I think as we continue to remove it from the system, at least some guys thinking the opposite way. So thank you very much for your time, and I'm happy to take questions.